Hello guys, this is the lecture that I promised to show you using what's called a flipped classroom. Today we're going to talk about convection. Let's see. Convection. We've earlier talked about conduction, where heat is transferred through collisions, but this time we'll talk about convection. And convection takes place because or due to that different temperatures forces substances into different densities. In cold and hot temperatures. So hot substances, or let's say you have a substance, if the substance is hot, it's going to be less dense, and if the substance is cold, it's going to be more dense. I'm soon going to explain exactly what I mean. Imagine that you have, for example, a gas. Let's say that you have air at room temperature. Room temperature. Yeah, let's say air. And then the air outside, for example today, is much colder than the room temperature, of course. We're in the winter. In the summer it might be different, but now we're in the winter, so the air outside is colder. If we think about the particle theory that we used earlier to explain heat expansion, we can understand why this difference in density exists in, for example, air. You can understand what happens. So let's have a look at that. So let's say we have the cold outside and we have a wall, and then we have the hotter inside. And then we start filling the outside with air particles. So grab a nice blue here. So these are then air particles outside. And you can see there's a cold gas outside, cold air particles, so they are stuck roughly together. And I think we're aiming for, how many do we have now? I think we're aiming for 25, 26 particles. You can count them if you want to. You can stop the recording and count them, but I think they're 26. Okay, there we go. And then yeah, we'll write here air particle, so we know what they are. Okay. When gases heat up, particles start to vibrate more vigorously. They start to move faster and they spread out. So let's do the same amount of particles, 26 particles in room temperature. We know that the distance between them are going to be larger. So we'll do 26 particles like this. So there's a few up here as well. Okay, perfect. Outside and inside. So inside the particles are spread further apart. So I'll create a container here. This is a container. It could be my sandwich box, for example, that I always bring, this letterbox. Let's say I scoop some air out of the room like this. You can see that I have 1, 2, 3, 4, 5, 6, 7 particles in my box. 7 particles in my box, and if I do the same thing here, try to fit as many particles as I can in. I don't know, there are 4. I think, yeah, 4 is probably going to be the best I can do here. So I fit 4 particles inside into the same box. The volume is the same, right? So there is, per volume is then more particles outside. I automatically fit more particles because particles outside are closer together. Oops. So that means, if you think about particle theory, of course, that the particle theory says that all particles are identical. They have the same mass. So if I fit 7 particles outside and 4 particles inside, and they have the same mass, then that must mean that didn't become very well. Let me change that. That must mean that I must have more mass inside my sandwich box from the air that I scooped outside compared to the air that I scooped inside. Let's see. So the same mass of, not all the particles, let me take that away. The same mass of the particles, the individual particles then, of course. So density, you know, is mass over volume. And the volume is the same. I use the same sandwich box, both when I scoop my air outside and inside. So the mass of the particles inside is less than the mass of the particles outside. Let me rewrite that. It's a better mass of the air in container inside is less than mass of air in container with the outside air. Now that looks a bit weird. Let me fix that a little bit so it looks better. There. Okay. Take that away. Okay. So the mass of the air in the container inside is less than the mass in the container outside. Therefore, the density of the container, the density of the air, the warm air inside, is less than the density of the air outside. And as we know, for example, if you have a look at sunflower oil and water, you know that sunflower oil has a lower density than water, and therefore sunflower oil floats on top of water. So that must mean that if the hotter air is less dense, it also flows on top of the cold air. So if you have air becoming hot, it flows up and puts itself on top of the cold air. So the same thing applies to hot and cold air. Hot air is less dense, floats on top of cold air. The less dense substance floats on the more dense substance. And of course I have to convince you of this, so I'm going to try to show that to you with a little demo that I prepared. We'll also have a look at the demo in class. So we're going to see I have created a paper spiral. Let's see. Here's the paper spiral, and the paper spiral is hanging in a small thread, and I put my hands under to heat the air. And as you can see, as the air rises from my hands up toward the ceiling, because my hands, the air that I heat with my hands has a lower density, the spiral is turning. And here I do the opposite. I have a cooling block or an ice block that you can put in your refrigerator, and here I put it above the spiral. The cold air around the cooling block gets the paper spiral to spin the other way. I'm soon going to show you the same thing again, see if I can get this moving. It was a little bit hard to hold it above, so I'm going to try another time, and this one I'm going to hold both below. So here's my hands again. Slowly it starts to move, right? So the air is rising. Now I'll take my cooling block, and you'll see here the second time I tried it's much more efficient to hold it beneath. You see how it turns and starts spinning the other way. Okay, that was it. That was my presentation of convection. The rest we take in class. See you tomorrow.